A viral post lately claimed that a mysterious force passed through the Milky Way without light, heat, or warning. The language was dramatic, but what are astronomers really observing? Recent research has concentrated on unusual high-velocity gas structures and stellar streams traveling through our galaxy's outer areas. Phenomena that are measurable and scientifically significant. The true story isn't about an invisible shockwave, but about how matter shifts through and around the Milky Way across cosmic time. In this video, we will explore what has truly been found, why it holds scientific importance, and what it reveals about our galaxy's structure and evolution. Let's begin. Discovery. The scientific observations behind the viral framing concern structures in the Milky Way's halo, the immense extended region encircling the visible galactic disk. Using large radio telescopes, astronomers chart neutral hydrogen gas via its 21 centimeters emission line. This method uncovers enormous gas clouds that remain invisible otherwise in optical light. Among the most examined of these structures are high-velocity clouds, or HVCs. These clouds can stretch thousands of light years and travel at speeds unaligned with the Milky Way's disk rotation. By gauging Doppler shifts in their radio signals, researchers can ascertain how swiftly these clouds move and if they approach or recede from the galaxy. Recent studies have emphasized coherent gas filaments and compact hydrogen clouds speeding through the outer halo. Some seem to fall inward, potentially providing the galaxy with fresh material. Others could be remnants of dwarf galaxies disrupted gravitationally in past encounters. Besides gas clouds, astronomers investigate stellar streams, elongated star trails remaining when smaller galaxies get torn apart by tidal forces. These streams can span large sky portions and act as historical logs of previous mergers. Their halo motion yields crucial details about the Milky Way's gravitational setup. None of these findings suggest a sudden impact event. Rather, they disclose a dynamic galactic setting molded by enduring gravitational interactions. The Milky Way isn't isolated. It resides in a network of satellite galaxies, diffuse gas, and dark matter structures that persistently affect its evolution. The mysterious force noted online probably mirrors a simplified view of these fast-moving structures. What scientists observe is matter redistribution and gradual accretion, processes key to galaxy expansion. Scientific importance and theories. Comprehending these high-velocity structures is vital for clarifying how galaxies maintain themselves. Star formation needs hydrogen gas. Across billions of years, galaxies deplete their gas reserves. Without replenishment, star formation would drastically slow. One primary theory posits that some high-velocity clouds stem from the intergalactic medium. Gravity pulls this diffuse gas toward major galaxies like the Milky Way. As it descends inward, it cools and ultimately merges into the galactic disk, aiding future star generations. Another account involves prior mergers. The Milky Way has engulfed many smaller galaxies throughout its history. When disrupted, these galaxies leave star and gas streams. Some HVCs might connect to these merger remnants. There's also rising interest in the chance that certain compact gas clouds embed within dark matter halos. If verified, these could signify dark galaxy candidates, systems ruled by dark matter with few visible stars. Their identification would aid in tackling the missing satellite issue, where models forecast more small galaxies than astronomers now see. Their presence would help resolve why. Dark matter plays a pivotal role in these dynamics. The Milky Way embeds in a vast dark matter halo reaching far past its visible disk. Gas clouds and stellar streams travel under its gravitational sway. By examining their paths, astronomers can deduce dark matter distribution across the halo. These observations also tie to what researchers occasionally term galactic weather. The Milky Way's disk displays ripples and warps probably stemming from past satellite galaxy interactions, like the Sagittarius dwarf galaxy. Such meetings subtly reform the disk without creating explosive events. The core insight is that galaxy evolution is ruled by gravity over vast time scales. The structures seen today echo cumulative processes, mergers, inflows, and tidal interactions that have formed the Milky Way across billions of years. Implications and what's next. The implications of these discoveries reach into various astrophysics fields. First, enhanced mapping of high-velocity gas flows refines our grasp of galaxy mass acquisition. If these clouds deliver hydrogen to the Milky Way, they sustain star formation and shape long-term evolution predictions. Second, monitoring gas and stellar stream motion yields indirect dark matter measures. Since dark matter can't be seen directly, astronomers depend on gravitational impacts. How clouds and stars traverse the halo provides limits on its shape and density profile. Current missions boost measurement accuracy. The Gaia spacecraft has revolutionized our stellar motion understanding in the galaxy, unveiling detailed stellar stream and substructure maps. Radio surveys persist in honing galactic halo hydrogen maps. Future tools like the Square Kilometer Array will vastly heighten faint hydrogen emission sensitivity. This will enable astronomers to gauge high-velocity cloud distances more precisely, clarify origins, and assess composition in finer detail. Researchers also merge observational data with cosmological simulations. These simulations depict galaxy formation in dark matter halos. By matching predicted gas inflows and merger histories to real observations, scientists evaluate current cosmological model precision. Another key frontier is discerning if certain clouds arise inside the galaxy or from intergalactic space. This demands absorption measures using distant quasars as backdrop light sources. When gas clouds cross quasar fronts, they imprint identifiable absorption marks that aid in determining distance and chemical makeup. For the wider public, these advances show astronomy's progress. Many astrophysical events are unseen in optical wavelengths. Hydrogen gas detects best in radio. Dark matter infers via gravity. Lack of visible light doesn't mean lack of comprehension. It just needs specialized tools. The Milky Way stays an evolving system. Satellite galaxies keep orbiting. Gas flows inward. Dark matter molds large-scale motion. Each fresh data set hones our grasp of universe structure formation. Ultra. What astronomers observe isn't a sudden invisible impact, but high-velocity gas clouds and stellar streams forming our galaxy. These structures show how gravity, dark matter, and gas accretion keep building the Milky Way. The real tale isn't dramatic. It's the consistent evolution of a galaxy growing still within the cosmic web. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.